Bismillah ar-Rahman ar-Rahim. So in the previous lecture, we were discussing some examples or design examples of MSI components. Okay, and we gave how many examples did we give? We gave basically a number of examples, starting with a 2x2 crossbar switch, and then sorting two unsigned numbers. Okay. And then we gave an example of an arithmetic logic unit. Actually, we gave two examples of that. Okay, one from the slides and one from an exam. You can see that this is a favorite question to ask in the exams. So pay attention to this question, okay? Pay attention to implementing arithmetic and logic units. And then we give an example of implementing decoders, okay? Decoder implementation of functions. This is not, by the way, this question here, question number, the question that is shown in the screen is not a trivial question, because having, for example, y2 as taken directly from x2 is an idea that may be surprising to some students if they haven't seen it so far, okay? So they will say, well, how do I get y2? By basically ORing, because we have 4 ones here, 4 minterms, okay? By ORing these minterms, but they will wind up with the wrong implementation because it's not minimal, okay? So the minimal way to do it is to take it directly from x2, because it equals to x2, right? Equals x2. Also, another note here is that you can implement this with instead of a 3 to 8 decoder, you can implement it with a 2 to 4 decoder, as you can see. Okay, why is that? Because if you inspect if you inspect the truth table carefully, it's going to be a function. All the functions are going, all the outputs are going to be a function of only 2 variables instead of 3 variables. Okay. So for example, y2 is only a function of x2, and y1 is basically not a function of x0, and y0 is also not a function of x0. Okay, so x0 is outside the equation, okay, completely. All right, so we can do it with a 2 to 4. So when the bottom line here, or the takeaway message, is when you get a question like this, take some time to check the patterns here. Check the patterns of the truth table and see if there is something that is special. Okay, you can directly see that y2 is neither a function of x1 or x0. Okay, and y1 as well, as because basically y0 is the complement of y1. Okay, so if y1 is not a function of x0, then y0 is not a function of x0 as well. Okay, so we know that y1 is not a function of x0. Why? Who can tell me why is y1 not a function of x0?
You cannot get any of them from the other.
You can see that.
So for example, I cannot get y2 from x0 by complementing or using
no. You can probably get part of the information, but here it's not a function at all, okay, of x0. So look at y1 and look at x0. Now x0 changes from 0 to 1 for the same values of x2 and x1, okay? Whereas y1 is a constant 1. So this tells you that probably it's not a function of x0 because x0 changes and y1 is not changing. Keep checking this for all of the patterns here. Okay, you see that for every pair of rows, y1 doesn't change. So this tells you that x0 is not a function of, or y1 is not a function of x0. It's indeed a function of x1 and x2 only. Why do I say x1 and x2? Because basically it's a function of x1 because it changes with x1, okay? And also the bottom part of the table is different from the top part of the table, so it's a function of x2. Okay, so let's draw a 2 to 4 decoder, okay, and see how we can implement the function with a 2 to 4 decoder now. So I have A1 and A0. These are the inputs. And I hook up A1 and A0 to where? To X2 and X1, right? Yeah, because I said X0 is outside the equation now, right? And
Okay,
then
should we say x0 and x1?
no, it's as I said. Okay, when you use a 2 to 4 decoder, x0 is outside the picture completely. Okay, because we said that all of these functions are not functions of x0. Okay, so this is a unique way of solving this problem. Okay, for y2 we take it directly from x2. This is y2. All right, just like the 3 to 8 case. Okay, and then for y1, okay, when we have 0 0, so it's when we have 0 0 for x2 and x1, okay, we'll have a 1 in a 1 for y1, right? So this is going to be what? This is going to be y1, okay, and when we have for y0, so let me translate this table, okay? It's better to translate this table in terms of x2 and x1, okay, and remove x0, okay? Remove x0. So we have y2, y1, and y0. So we have 0, 1, 0, 1, and then 0, 0, 1, 1. All right? So when we have 0, 0 for x2, x1, what is y2? It's 0, right?
0.
And the second row is 0 as well. No, it's
It is 0.
yeah, it is 0. Yes, yes. I was looking here, which is wrong. Okay, 0 and then 1 and then 1, right? So it is indeed x2, right? Just like
Doctor, it's four zeros. It's for y2.
yeah, but we removed x0 now. We removed so now we have only 4 rows for the truth table.
Okay.
As
yes,
I said, x0 is not affecting the functions here.
Yes.
Okay, so y1 now will be what? Well, let me just erase because these are confusing us. Y1 is going to be what? Is going
0,
to be
1, 0, 1.
Actually 1 here. Okay.
Oh.
At the beginning 1, and then the rest are
0.
zeros, right? And y0 is going to be the complement of y1, right? So where do I get y1 from in the 2 to 4 decoder? I get it from Minterm number 0, right? Minterm number 0 here in the 2 to 4 decoder. Do you see that? So now it's You came up with the truth table, the minimal truth table, okay? And it's the only job that you do is to map this to a decoder now. For Y2, I said we take it directly from X2. We don't need a decoder for that. For Y1, we take it from Minterm number 0. And Y0, what about Y0? We can either OR these together to get it, or we can just complement Y1, right? So this is the minimal way of doing it. You see that? We are not using any other
Doctor,
of the decoder. Yes.
for Y1 and the new truth table, how would it change to 1 3 zeros?
Okay. Look at the original truth table now and tell me when we get rid of this column there, of this column. Okay, when
Yes.
we get rid of this column and then make the table unique. So this column here, if you get rid of this column, you get 0, 0 twice, right? So just combine them, okay, and then you get here 0 twice. You combine them, you get a 0. Okay.
Yes.
You're talking about Y1, right? Y1.
Yes, I'm talking about Y1.
So here you get a 1 for these two 0 zeros, and here you get 0 just once for these 0 1, and here you get 1 0 1 0. You get a 0, and 1 1 1 1. You get a 0. That's what we did here exactly. So this is repeated twice, but we are not showing the repetition here. It's 0. Okay. Because we said that X0 is not affecting the functions here.
Yes.
You get that now?
Yes, I see it now.
Okay, great. So this is the other way of solving the question here. Any question about it? Or shall we move to the next level? Okay, because the next one will be more challenging. And it's also an exam question. By the way, just to let you know, okay, in the exam, we accepted both solutions, this solution as well as this solution. Okay, some smart students came up with this solution. Okay, I hope you guys appreciate this. Okay, so just imagine that we used to have students who can come up with this solution by themselves. Okay,
used to have.
Hopefully we still have. Okay, hopefully. I'm just trying to motivate you guys. Okay, I'm trying to motivate you to study. I mean, this level of thinking, okay, requires a lot of practice. It doesn't come because the student is smart. It doesn't come because only the student is smart, but it also is an indicator of hard work as well. Okay, so please work harder and try to solve as many problems as you can to be on the A+ side. Okay, right now you guys are in the B+ side. Okay, because the other sections are better than us. So please, I'm trying to motivate you to study harder for the final exam. Okay, otherwise, the exams are common, and we have to, if other students are better than us, they will take the better grades. So I'm just telling you. All right. So this question here is interesting. Let me just erase the answer because I want to develop the answer with you guys. Okay. All right. So what does the question say? I want to give you a minute to read the question, okay, and then come back with your questions about the question. Okay, I'm going to pause the recording now, and then come back in a minute. So give yourself some time to read the question, and then I'm going to come back in 1 minute. Okay, I'm back now. Any question about what to do? You guys are clear on that. So let me ask this: what is the purpose of this problem?
Find to find the maximum of three numbers and the minimum, then subtracting them.
Excellent. Find the difference
The
between the maximum and
minimum
the minimum of three
4-bit unsigned numbers.
Excellent. That's exactly what it is. Okay. And also we are giving you some constraints. You're going to only use inverters, okay,
and MSI component.
and MSI components. That's it. All right. And you cannot use subtractor as a component. You have to use an adder for that. And we mean like excuse me, subtracting using 2's complement. Okay. So I'm going to solve this problem. The solution of this problem is there in the blackboard. Just look at it. But I'm going to solve this problem in a different way. Okay? All right. So we have seen how to do a sorter, right? Before this one. This is nothing but a sorter, right? That produces the minimum and the maximum of two numbers, right? So I'm going to, so this circuit here satisfies the conditions, right? That are basically specified before. So it uses MSI components, comparators, multiplexers, okay? And nothing else, right? So I'm going to denote this circuit by a big box like this, a black box, right? That accepts A in 4 and B, are both 4-bit A. I'm not going to write the subscript like this, okay? So just A and B, right? And then it will produce, let's say, max and min, right? Max and min. So let's call this, actually, it's the other way around. So min and max, just to
Isn't this like the magnitude comparator?
Yeah, it's just I'm just trying to create a symbol for the whole thing, okay? For the whole thing to use it, to reuse it in our problem, okay? So this is a min, this is sorter. Let's say 2 sorter, okay? 2. Let's just call it 2 sorter, which takes 2 numbers and sort them, minimum and maximum, okay? So the minimum is also 4-bit and the maximum is 4-bit, okay? So now, in order to simplify my solving of the problem, I'm going to use this block here, this block, to build a 3 sorter. Okay, do you get what I'm saying? So now 2 sorter. Okay, let's call it. Let me call it a better name. Okay, it's called min max 2. Okay, A and B. It gives you 2 numbers, min of A and B, and max of A and B, right? Yeah. So it gives you 2 outputs. This is the first output, and this is the second output, right? I'm calling the circuit min max 2 here because I would like to implement min max 3. This is why I'm calling it's better than saying sorter to 2 sorter or 3 sorter. Okay, min max 3 now, which takes 3 inputs, A, B, and C. All right, is going to be what? we will use the min and the max to define our variable, to define our min max 3. Okay, so in essence, okay, so let me backtrack. Okay, let me backtrack a little bit, or back off a little bit. I'm going to use not this min max, but rather I'm going to use min, the min and the max blocks. Okay, so I'm going to create two blocks. One is called min, okay, that outputs the minimum, and it takes two variables, a and b. All right, and the other is a max block, so I can call this min2 and max2. All right, and it produces a max. Can you create these two blocks yourself? I'm asking you guys, can you create these two blocks for yourself? We have seen a more difficult circuit before, okay, which produces the min and the max together. So this is nothing but a subset of this circuit here.
But doctor, how are these blocks connected to min max 2?
Forget about min max 2. We're not going to use it.
Okay.
Okay, we're not going to use it.
Yes.
Okay, so we have two blocks now. Man 2, which is a function of a and b, will produce for me min of a and b. Okay, and max 2 of a and b, okay, will produce for me the max of a and b. Okay, can you tell me how can I implement these two functions, these two blocks? From your knowledge, what do I need? Because you need to be able to implement them in order to solve the question, right? We have seen the sorter before, right? Sorter basically contains the answer. So this one here, this part here is for the min. Okay, any part that belongs to this output is for the min. Okay, so you need the comparator anyway. Okay, and this multiplexer will give you the min, and the comparator with this multiplexer will give you the max. You see that?
Yes.
It's very simple. Okay, so this is the implementation of these two blocks. You get it, you have it somewhere. Okay, but in the exam, if you give it like this, it will not be accepted. You have to show the implementation as well of these two blocks. Next, we are going to implement min 3 of a, b, and c in terms of min 2. How can I implement that? Who does have an idea? If I want to find the minimum of 3 numbers, given the function that that calculates the minimum of 2 numbers, how do I do that? This equals to min 2. You can continue. Okay, min 2 of what? A.
Of min 1 and c.
What's that?
We take the minimum of the first block with c.
Yeah, like this, for example. Associativity, you know. Yeah.
Yes.
So whatever order you want. Okay, min 2 of min 2 a and b and c, or min 2 of a, comma, min 2 of bc. Both works fine. Okay. Next, this is check. Okay, so min 3 is implemented. You know how to implement it. Okay, because we know how to implement min 2. It's using only min 2 here. You see that? Okay, what about max 3? A, B, and C. It's the same, okay? Max 3, A, comma, max 3. Anyone who's not convinced about this? So we want to find the minimum of 3 numbers. Okay, basically, what do? We find the minimum of, for example, you have
Isn't it
5.
max 2, doctor? Inside.
Let me finish this idea, okay? Let me finish this
Okay.
idea. Just the behavior of min 2, min 3, and max 3. Okay, so you want to find the minimum of these 3 numbers. What do you do? As a computer, what do you do?
Take the first two, compare them.
Yeah, take any pair, pick any pair, like this one, for example. Pick its minimum. It's 5, okay? And then pick this pair that is remaining here, okay? And then pick its minimum, which is 5. This is what we are doing. And in fact, what we are doing is not like this. It's 5. Let's say here 4 and 8. Okay. What we are doing is to take the minimum of these two, okay, which is 4, and then take the minimum of 5, which is the remaining one, with 4. So the minimum, the global minimum is 4. Okay. But you're right. You're going to need a multiplexer here as well, because actually you don't need a multiplexer. For the implementation of max 3, all you need is this is min max 3. This is min 2, not min 2. All right, not max 2. I'm sorry, max 2. For the implementation of min 3 and max 3, you don't need a multiplexer. Why? Simple, because all you need is these blocks here. So you have a min 2. For example, let's see how a min 3 is implemented. Min 2 here, and you have another min 2 here. So here, for example, you get B and C, 4 and 4, yeah, and here you pick this, okay, which is 4 as well, and you pick the minimum of this with A, and this is going to be the minimum of A, comma B, comma C. You see that? The multiplexing is inside these blocks, okay, inside of here and inside of here, okay.
Do you mean the magnitude comparator to multiplexers?
Yeah, of course. Yes, you'll need a magnitude comparator here and here as well.
I have to show that before implementing this, right?
Come again? Yeah, you have to show it. You have to show the implementation of min 2 and max 2, and then min 3 and max 3.
But min 3, max 3 will be just the same as min 2 or max 2.
No, it's not the same. It's using them like this, okay? You mean like a block?
Yes.
Yeah, I mean, you can do that, but it doesn't have to be. Anyway, so let's say that you done it like a block. So how to solve the problem now? You have min 3, or let's start with max 3, okay, and then min 3 as a block. So this takes A, B, and C and produces the maximum of them. And this takes A, B, and C and produces the minimum of them. What is remaining? All of them are 4 here.
Subtract the max from the min.
Yeah, how do you do the subtraction?
It's a ripple carry adder, but you will complement the literature and add 1 from the carry in.
Excellent. Yeah, this is a 4-bit adder, or you can say RCA as well. This is your A and this is your B, and this is 4 as well, and this is 4, and this is 4. Okay, So the inverter here is a bitwise inversion, and the carry n here is 1, okay? Because you need a minus b eventually, and the result here, which is 4, the result will be what? Your C. So this is the circuit. You get it now?
Yes.
You must understand this because most likely I'm going to give you your next Verilog assignment based on this, okay? So you must understand how to solve this in order to solve your assignment in the next Verilog assignment, okay? Okay, any question? Please also review the answer in the solution key. The answer that is given is different. It's not different, in fact, it's the same, but rather than doing it hierarchically like this, they are doing it starting from the comparators and multiplexers, okay? They're showing the implementation using standard MSI blocks, okay? Okay, this is a question from the previous term exam of Dr. Mudawar, okay? He's asking, he wants the minterms for the functions provided here. Okay, the minterms for the function provided here. Okay, and sigma notation. So who can tell me what are the minterms for F1? This is a decoder, by the way. This is a decoder, a 3 to 8 decoder with enable. And enable is always 1.
So it's 4 and 2. It's actually a max term of 4 and 2.
What's that?
Max term of 4 and 2.
Yes, the max terms are 4 and 2. So the minterms, which is the question, sigma notation.
So 0, 1, the other letters also.
Yes.
0, 1, 2,
okay.
3.
What about this one? You see the enable here is 0, but it has a bubble. So the bubble, this bubble means it's active low. So 0 means it's enabled. Okay. What about this one? F2. What are the minterms there?
They are connected 3, 2, 1, 0.
Yeah, but you have bubbles at the output, you see?
So it is
Which is this, a max term?
4, 5, 6, 7.
Max terms, yeah. So who answered?
It's me. I said it's the others that are not connected. 4, 5, 6, 7.
Yes, excellent. Yeah, it's 2, 4, 5, 6, and 7. Yes. Okay. All right. Moving on to the next one. Okay, so this is a more advanced, so it requires a little bit of understanding of the decoder expansion. Okay. What are the minterms for F3?
They're bubbled twice, so I'm guessing 1, 0, and 2.
Yeah, so here when you have a bubble at the enable, okay, that means it is enabled when it is 0. Okay.
But there is an inverter, so.
Yes, but there's also an inverter before.
Okay.
So it's just like so it's cancelled out.
Which decoder? Let me ask you this: which decoders is is related to the top part of the truth table. Is it the lower decoder or the top decoder?
It would be the lower.
I want a definite answer.
Because if A is 1, it will invert and then it will invert again.
Yeah, so it's definitely the bottom decoder. So if A is 0, the enable will be the bottom decoder will be enabled, and then these will be minterm 0. This is minterm 0, and then or max term 0, basically max term 0. This is max term 0. Okay, max term number 0, right, and then 1, and then 2, 3, and then here you get max term number 4, right? This is the second half of the table, yeah, and then 5, and then 6, and then 7. Okay. All right. Now, isn't it easy to see what is F3 now?
Yes, it is here.
It is.
Is it 0, 1, 3, 4, 5?
No, it's not. I'm sorry.
It's M3, M4, and 5.
No.
Well, I'm not saying it.
Which
That's all.
M3? Which M3? Are you talking about max term or min terms here?
Well, max terms will be inverted, so eventually it will be minterm 3, 4, and 5.
Did you notice the bubble here?
Yes, that's why I'm saying it will be a minterm.
So
Yes.
so
Yes.
it will be
So what does this belong to?
2. Is it 2, 6, 7?
No, it's 2,
So
4, and
4,
5.
5.
Yeah. You get it now? Okay.
Yes.
Well, this is a
I think
tricky
so,
one,
yes.
but it's so I'm done here. I don't think there is time to take another problem, but let me just pause for a second and ask you if you have any question about whatever subject about the previous chapter here or unit.
Yes, Doctor. I was confused about one part where we implemented a demultiplexer using a decoder. I tried going through. Yes.
Which part? Is it one of the problems or?
No, it was before we started the problems. How to implement a demultiplexer using a decoder.
Oh, okay. Yeah. Okay. Any Boolean function
Can be represented by decoder. Yes, I understand.
Yeah. So no. So you want to know what is the how is the demultiplexer related to the decoder with enable, right?
Yes.
Okay. So we have here a decoder. It's not a good decoder. Okay, we have A1 and A0, and we have the enable. Okay. Let's say that this is, for example, little a1 and little a0, and this is my, I'm going to call this input I, okay? And this is a 2 to 4 decoder with enable, okay? And this is output number 0, number 1, number 2, number 3. All right. Now I want you to tell me what is the functionality of this decoder, or what is the output of this decoder when I is 0.
Be all zeros.
All zeros regardless of the input. Okay?
Yes.
Right? So let's say here that when I is 0, okay, we will have output, which is, let's say, we called it before D, I believe, yeah? the output will be 0. Okay. And when I is 1, what is the output?
The minterm of whatever A1 and A0 is.
2 to A, right?
Yes.
Yeah, 2 to A, right? Isn't this, so what are we doing here? We're taking this one here, which is I, okay, and forwarding it to output number A. So it's also a demultiplexer in this sense. Okay, so what is the definition of a demultiplexer? Definition of a demultiplexer, behavior of the demultiplexer. It takes one input I, okay, and selection lines S1 and S0. Okay, in this case, I can call them A1 and A0, and then we have this is a 1 to 4 demultiplexer. Okay, 1 2 3 0 1 2 3. Okay. So this one here, if this is a 1, okay, is forwarded to one of the outputs, okay? Which output is it? It's output 2 to A, right? So in order to be consistent, just to be consistent here, okay? This is going to be a 0 times 2 to A, right? And this is going to be a 1 times 2 to A, okay? So we are here forwarding a 0 to output number A, and here we are forwarding a 1 to output number A. So in general, the output of the decoder with enable is going to be I into 2 to A, which is exactly the functionality of the multiplexer, demultiplexer, I'm sorry. So the demultiplexer, what does it do? It forwards this bit to output number A, okay? So this, remember that this is either a 0 or a 1. It's not an integer. It's a 0 or 1. It's a binary, okay? So it's either all zeros or it's exactly this power of 2. You get it, Abdullah?
Yes, I kind of got it. Yes.
You kind of get it, but you have to go back and study, please, okay?
I studied all the subjects actually, but I thought the decoder, we are just producing whatever minterm we get from A1 and A0. So that's why, but I see the point.
Yeah, but believe me, Abdullah, you will, if you don't keep studying and practicing, okay, and seeing where this is coming from, you will forget. Okay, you will forget because it's too much. Okay, you have to move this chunk of information from the shallow memory to the deep memory. Okay, by practicing more and more. Okay.
Yes, I will.
Let me stop here.